All right, here we go. Lesson 10.3, solve an exponential and logarithmic equations. So one thing that you need to make sure you pay attention to is to make sure we have to say if it's a one-to-one property, if we can use that one, or if we're going to have to use the inverse property. So if it's a one-to-one property, you will have the same base here, okay? Same thing here if you have a logarithmic. You'll have the same base. So in a one-to-one property, if you have the same base, whether it be exponential or log, then you can just simply say that the exponents equal each other, or whatever you're taking the log of, that they equal each other, okay? If it's the inverse, which I did not have to do these a while ago, but I used all of the exponential and the logs. I just made the same base. That just was the easiest for me. But here's what the inverse property says, okay? All right, so it says to look at or as you solve the equations, look for patterns that emerge. We're going to talk about the patterns on the next page, but let's go ahead and solve these. So this first equation, it's in an exponential form because we have a base to the exponent. And so since they do have the same base, it would be a one-to-one. So let's go ahead and make note of that on our notes, that it is same base. So one-to-one property. Okay, so we get to use the one-to-one property on this one. Okay, so because they have the same base, that means I can take the exponents and set them equal to each other and then solve. So 3x minus 2 equals negative x. And so I'm just going to solve this for x. That's all we're doing here. So I'm going to subtract 3x to both sides. And you get negative 2 equals negative 4x. Divide by negative 4, divide by negative 4. So x equals positive 1/2. Okay? And so that would be our answer there. All right? So when you have the same base, it's a whole lot more it's just a lot simpler, which is why when I did mine, I just made sure it was all the same base. All right, moving along to the second example, they both are log base 2. And so we're good there. They have the same base. So again, I'm just going to make notes so that way we get in the habit of checking it. It is the same base. So one-to-one. Okay. So then that means that I can say, okay, well, negative a minus 3 equals a squared minus 33. Okay, now, unlike the last problem we had, we did not have an exponent of 2 in any of our variables, but on this one we do. So when you see the x squared, just as a reminder from the last unit that we did, if you have the variable squared, you're going to have to factor that. All right, so I'm going to get everything on the same side. That I'm going to move the negative a and the negative 3 to the other side. It should be a plus 3, sorry. So I add a and I add 3. So I get 0 equals, and so that's going to become a squared plus a minus 30. So I need to factor this. So I know I need to multiply to give me negative 30, but add to give me a 1. So that's going to factor to a plus 6, a minus 5. Okay, so that means that a can be negative 6 or 5. Now, when you have equations that have log whatever, okay, as a reminder from the last section that we did, or not the last section, but in section 1, log does not have a domain of all real numbers. So we do have to check for extraneous solutions here. And so what we're going to do is we would just say, okay, well, we would plug it in. Log base 2 of negative a, so of negative 6 minus 3. And does that equal, I guess I'll just write it right underneath. Log base 2 of negative 6 squared minus 33. So obviously negative times a negative gives us a positive. So this would just be log base 2. If I do positive 6 minus 3, I get a positive 3. And then I have log base 2. Negative 6 squared is 36, and 36 minus 33 gives you 3. So these two equal each other. So negative 6, will be a solution, but now we need to check the 5. So we're going to say, okay, well, log base 2 of negative a, so negative 5 minus 3. Oh, I'm running out of room, sorry. And say, well, does it equal log base 2? Oh, wait, I'm sorry. Of 5 squared minus 33. And so when I simplify what's inside of the inside of the parentheses, I get log base 2 of negative 8 equals log base 2 of, what is that, negative 7? But you can't take log of a negative number, okay? So I can't, making a note here. So can't take log of negative. So because of that, that means that 5 is an extraneous. So the only solution that we have here is that a equals negative 6. All right. Okay, so moving right along, we have, again, they both have the same base, so we're good there. So we just say, okay, x minus 2 equals 5x minus 7. So I'm just going to solve this for x. So I get 5 equals 4x, and when I solve for x, I get that x equals 5 over 4. But because this is a log function and not an exponential, I need to double check this, that this does not have an extraneous solution. And so I'm just going to plug it in again. So I would say log base 4 of 5/4 minus 2 equals log base 4 of 5 times 5/4 minus 7. And so again, 5/4 minus 2, that's going to be log base 4 of negative 3/4 equals log base 4 of, what would that be? 25 over 4 minus 7, which is going to give us a negative value, which we already have a negative value over here. So that means that extraneous solution is right here. So this one would be a no solution because we don't have a real solution. We only have extraneous solutions. All right. And so then we move on to the last one on this page. And so they have the same base. This would be an exponential function. They have the same base. So we're just going to take the exponents, 4x minus 7, and set it equal to the other exponent, negative 37 plus 7. Or plus x, excuse me. And so I'm going to move the x to this side, and I'm going to move the 7 to the other side. So we get 3x equals negative 30. So when I divide by 3, I get that x equals negative 10. And I'm going to actually write the kind of reminder of this. But since this is an exponential, oh, I'm misspelling that. Let me spell it right. Exponential. So exponential function, no need to check. Because domain is all real numbers. Okay? All right. So let's move on to the second page. So remembering kind of what we just talked about as far as if they have the same base, being it whether it be exponential or log, if it has the same base, then it's much easier to solve, if you will. So if I know my squares, I guess, or my powers of 5, I know I can rewrite this number 25. I can rewrite it as 5 squared. So I'm going to rewrite that as 5 to the 4x power, and it's going to equal 5 squared. And the reason I rewrite that is because now I have the same base. So because I have the same base, I can just say 4x equals 2 and then solve it for x. And so I would get that x equals 1/2. Okay. Now there's going to be times that you can't do it that way, like this one here. And there's no way to rewrite 0 as the natural log to a power or something like that. But what we do know is that the natural log has a base of e. Okay, we talked about that in section 2. So the natural log has a base of e. So I can rewrite this in exponential form using what we talked about in section 2 as far as circle of life. I can rewrite that as e to the 0 equals x plus 2. Now my exponent rules tell me that anything to the 0 power equals 1. So I can say that 1 equals x plus 2 and then solve this for x. So I'm going to subtract 2 to both sides, and I get that negative 1 equals x. Okay, now you can check it if you need to by saying the natural log of negative 1 plus 2 equals 0, which would mean the natural log of 1 equals 0. And that is the case. Okay. All right, so now on this one, and they have it written as the same base here, and they're actually adding these two logs together, the logs being that they have the same base. So whenever you can rewrite this because of the product rule, or kind of the opposite of the product rule, is whenever you add something, that really means that they were being multiplied. So we could say log base 8 of x minus 3 times x plus 4 equals 1. Okay, so, and the way that I was able to write this from expanded form to condensed form is what we talked about in section 2, being that we know the log or properties of logs and we can rewrite it like this. Okay, now I'm going to convert this though to exponential form. So to do that, I'm going to say the base, excuse me, of 8 to the first power times this, or equals this, excuse me. So I'd say, well, 8 to the first power equals x minus 3, x plus 4. Now I will need to either FOIL or box method the x minus 3, x plus 4 out. But 8 to the first power gives me 8. And so then that would be x squared plus x minus 12. I don't know why I put it in parentheses, actually. Okay, now because it says x squared and we have a second power, we are going to have to FOIL that, or factor that, but first I need to get a 0 over here. So I'm going to subtract 8. So really I have x squared plus x minus 20 equals 0. Okay, so I need to factor that, and so when I factor it, I would get x minus, or plus 5, x minus 4. So that means that x can either be negative 5 and or positive 4, but I need to check my extraneous, check for extraneous solutions. Okay, and so I'm going to write it in purple here. I would say, okay, sorry, this purple box is going to be where I'm checking. So log base 8 of negative 5 minus 3, okay? And you could continue on into the plus log base 8 of negative 5 plus 4, but I already know that this right here is going to give me negative 8. And I've already said I cannot take the log of a negative number. So negative 5 is going to be extraneous. But then if I plug in the 4, I have log base 8 of 4 minus 3. Well, that's positive, so that's fine. But then checking this log of 8, or base 8, excuse me, of 4 plus 4, well, that's still a positive number, so I'm good there. So my 4 would, in fact, be a real answer. Okay. All right. Moving on to this next example. Again, knowing my powers, I know that there's somehow I can rewrite 64 as 4 to a certain power. And so honestly, just to rewrite it, I would, if I don't know it off the top of my head, I would just play with it in the calculator. So I may say like, okay, well, I know 4 squared gives me 16, so it can't be squared. Well, let's check 4 to the third power. And so 4 to the third power is 64. So I'm going to rewrite that as, so I would have 4 to the negative n equals 4 to the third. And then because they have the same base, I can now just say negative n equals 3. And then I'm going to divide by negative 1 here to give me the n equals negative 3. Okay, and so because this is an exponential function, I do not have to check for extraneous. Okay. All right, moving into the next set of different examples. So I need to still solve this for x. Oh, excuse me. Hang on, let me get my notes all situated. Okay. Okay, yeah. So before I can do anything as far as solving for the inside of this, like this 2x here, I have to go ahead and isolate. It's kind of like whenever we did absolute values. You have to go ahead and isolate this, get the natural log of 2x by itself. So I need to subtract my 6 first to both sides. And I get that 12 equals 5 times the natural log of 2x. And then I'm going to divide by 5. Oh, wait. No, not 12. You should get 6 equals that. Sorry. And then I'm going to divide by 5 on both sides. So I get, well, the natural log of 2x equals 6/5. Okay. Now from here, I can convert this to exponential form to solve for x. Okay, because I can't just bring out this 2x in any way because you can't break up the natural log in the 2x unless you convert it to exponential form. So as a reminder from section 2, the natural log, the base is e. So using the circle of life, I'm going to say, okay, well, e to the 6/5 power equals 2x. Okay, so now I can solve for x pretty easily. Just bringing, I didn't mean to write a 6. Just bringing that over here, I would say e to the 6/5 equal 2x. So to solve it for x, I just need to divide by 2. Kind of flipping my equation around here, I get the x equals e to the, no, I'm writing it wrong, sorry, 6/5 over 2. Okay, so x would equal e to the 6/5 over 2. The whole thing. Okay. All right. Okay, so again on this one, I need to isolate. So this right here is all together. Okay, the 2 is being raised to the 3x power, and so I'm going to have to isolate that before I can do anything. And so what I would need to do first is I need to divide by 5 on both sides. So I get 2 to the 3x power equals 4. Well, again, knowing my powers, I know that I can rewrite 4 as 2 squared. So I'm going to say 2 to the 3x power equals 2 squared. And because they have the same base, that means that 3x equals 2. So to solve for x, I'm going to divide it by 3. So that means that x equals 2/3. Okay. And I will tell you before I keep going, up here, if you wanted to do the inverse and mess with this log stuff, you can do that, but it is just so much easier if you just get the same base. It's just a lot easier. So, but if you know that way and you're more comfortable with it, get after it. It's obviously not going to be counted wrong because it's still a way you can do it, but I like to work. I'm going to work hard, but I'm going to work smarter, not harder, if I don't have to get the same answer, okay? All right, here we go. So on this next example, I do need to move the 2 over to isolate that exponential thing there. So to do that, I'm going to divide by 2 on both sides. And so that would give me 8 to the 2x plus 1 power equals 64. I know I can rewrite 64 as 8 squared. So that's going to be 8 to the 2x plus 1 equals 8 squared. So because I have the same base now, I can just say, well, 2x plus 1 equals 2. Yeah. And then minus 1. So I get 2x equals 1. And when I divide by 2, I get that x equals 1/2. And that would be our answer. Okay. Okay, so on this one, before I can do anything, I need to isolate this log function. So I'm going to subtract 5 from both sides. And I get log of x minus 3 equals 2. Again, my log is a base of 10. So I'm going to go ahead and do the circle of life here to convert it to exponential to say, okay, 10 squared equals x minus 3. Well, I know that 10 squared is 100, so I know 100 equals x minus 3. And so when I add 3, I get that x equals 103. Okay. So each of the set of 4 questions has similarities. And so we're going to use this list of strategies used for each set. So one thing that we know is if they have the same base we're going to use the one-to-one property. And so what that meant was like if I had 3x equals, or 3 to the x equals 3 to the, 2x plus 3, I could then take my powers and say, well, x equals 2x plus 3. Okay, we don't have to go through and solve that, but we could do that. Okay, that's what one-to-one was. The next strategy that we have is that we could rewrite as exponential or logarithmic. Or we could just rewrite it with the same base and then apply the rule we just talked about with the one-to-one. Oh, wait, not as, but with. And then the last strategy that you could use is to use the inverse to undo exponentiation exponentiation, sorry. That's the word. Or logarithm. And so the last one we did that on, where it was already in log, but I know the inverse of log is exponential, so I just rewrote it as an exponential to solve it. Okay, that's that strategy there. Okay. Okay, so these next problems are just going to be some more examples using those strategies that we just talked about. I will tell you on my actual paper copy, I had to get a piece of paper out on the side to do some of the work because it had more work than what was allowed, the space that was allowed on the paper here. So I'm going to try to write small enough where I don't have to do that on this. But oh, yeah. Okay, so on this one, I know I can rewrite this as 2 to the 5th. Again, if you don't know what power it needs to go to, just kind of play with it in your calculator. So that means I have 2 to the x equals 2 to the 5th. Since they have the same base, that just means that x equals 5. Okay, so I can just do it that way. All right. So on B, first I need to isolate this. I'm going to divide by 3 on both sides. And I'm going to put over here. 2 to the x equals 14. Now, at this point, this is where I won't lie, I kind of was like, what the heck am I going to do from here? Okay, I know there's nothing I can raise 2 to give me a 14, and there's no power I can do. So what you can do, though, is you can just make both this and this here have the same base. Or same, like you can put it as a log to a certain base. Now, I will tell you, on the answer key from Tarleton, she uses like log base 2. I used ChatGPT to help me on this one. I'm not even going to lie to you. And their suggestion was just to use like natural log, something that already has like a common base. And you're more than welcome to use a different base, but this was just easier for me. So what I did is I said, okay, well, I'm going to say the natural log of 2 to the x equals the natural log of 14. Okay, and the reason that we can do that, the reason I did that is because they have the same base and it's super easy from there. But because this 2 to the x is a power, I can use my log properties and move my x to the front and separate it. So I would say, well, x times the natural log of 2 equals the natural log of 14. Okay? Now, all I need to do now is I'm going to separate these because that's being multiplied. I'm going to divide it by the natural log of 2. Okay? And so that just means that x is going to equal the natural log of 14 over the natural log of 2. Okay, now in the instructions, it tells you to give the exact values. This is the exact, but then it also tells you to give a decimal approximation up to 3 decimal places. So you can literally type this in your calculator. Okay, natural log, remember, is the LN button. And so whenever you do that, that means that x is approximately 3.807. And it does not matter what base that you used. Okay, like Tarleton used log base 2. I used natural log, and I still got the exact same answer she got here as the 3.807. And so to me, it just makes better sense to use a common base versus using like log base 2. Because like I told y'all can't even put that in on your calculator since it's in test mode in the classroom. And so I would go ahead and just use something that's natural, okay, or that's a common base. And so that's why I just picked, the natural log on this one, okay? All right, so on C, again, I need to isolate this before I can do anything. So I'm going to have to add 4 to both sides. And I get, 2 times 3 to the 2 times t minus 5 power equals 15. And so I'm going to divide it by 2. And I get 3 to the 2, or 2 times t minus 5 equals 15 over 2. And so again here, there's no way that I can like rewrite this 15 over 2, or it's somehow a base of 3. But I can say, okay, well, the natural log of 3 to the 2t minus 5 power is the same as the natural log as 15 over 2. And so when I do that, I'm able to move my exponent to the front. So 2t minus 5 times the natural log of 3 times the natural log of 15 over 2. Okay. Now I am going to show you the 2 different ways that you could do this one. Because after I worked through this one, I realized, oh crud, the other way might have been actually a little bit easier. But I'm going to keep going the course because it doesn't change your answer. It just kind of makes it not so crazy, okay? And so for right now, since that's being multiplied, I'm going to divide it by the natural log of 3. All right, I do have a little bit of room. So I'm going to go ahead and move. Well, I'm going to have 2t minus 5 equals natural log of 15 over 2 over natural log of 3. So I'm going to move this up here. Okay, so I know I need to add 5. So I'm going to have to add 5 to the back. And I get 2t equals natural log of 15 over 2 over the natural log of 3, and the whole thing is adding 5. Then I need to divide by 2, so I'm going to have this whole thing divided by 2. So t equals the natural log of 15 over 2 divided by natural log of 3 plus 5. The whole thing is over 2. Okay, now, so this is kind of messy. Oops. That. It's kind of messy, like there's just a whole lot of fractions there. And so, oh, hold on, actually, I'm sorry, I need to find the 3 decimal places. So 3.417, okay? I'm going to go ahead and show you what the, if I was to use a different base. And so let me show you that. In order to do that, though, I do have to erase this. So just know that. I'm going to have to erase this. So make sure you have that down. If you don't have this down, pause this video before I erase all of it. Oh, man. I need to erase this. So we would do the same thing up until we isolated where it said this right here. Oh, I'm going to have to write that 15 over 2 again. Okay, so we would do the same thing to this point. But if I remember, and I didn't remember this, even though I worked this like an hour ago, if I have log base 3 of 3, that cancels to a 1. So what I'm talking about is this thing right here. Log 3, base 3 of 3. This is going to cancel to a 1. Okay? So then I'm going to convert this to having a log base 3 of 3 to the 2t minus 5 power. It's going to equal the same thing over here. We have to have the same base. Log base 3 of 15 over 2. Because when I move this exponent out, I get 2t minus 5 times log base 3 of 3 and equals log 3 base 3 of 15 over 2. And so the reason that I would want to do that is because this is going to go away to a 1. So then I'm going to have, I'm going to write over here, 2t minus 5 equals log base 3 of 15 over 2. And so I would just solve it the same way I just did the other. So 2t equals log base 3 of 15 over 2, all of that adding 5, and then I would just divide it by 2. And get t equals log base 3 of 15 over 2 plus 5, all of that over 2. And this is going to give you the exact same answer. So either way you want to work that is fine. It's honestly just a personal preference at that point. Now, I will tell you that is the kind of craziest one out of all of these on this page. Really, the rest of the notes, if you will, actually. And so just know that the rest of them are not that crazy. All right, so I have e to the x plus 5 minus 7. So I need to subtract 5 to both sides before I can do anything. So I get what e to the x equals 2. Okay, and so I'm just going to convert both of these to have the natural log. So that's going to be the natural log of e to the x equals the natural log of 2. And the reason I do that is because now the natural log of e equals 1. Okay, and so that means that that's going to be 1 equals the natural log of 2. Okay, not 1, I'm sorry, x. Sorry, I wrote the wrong thing there. X equals the natural log of 2. So that means, so this is the exact version, or the exact form. Or you could say it is approximately 0.693. Okay, and that could be your answer. Okay. All right, on this one, we're actually going to get it where the natural logs are not on the same side. Since they already have the same base, so I'm going to add the natural log of 3 to both sides. I'm going to get the natural log of x equals the natural log of 3. Well, they have the same base. Look what matches. So that means that x equals 3. Okay. Now, obviously, on this one, you don't have a decimal form. So you have the exact and the decimal in the same. All right, moving on to F. Sorry, I got distracted. So natural log of x, it's already in a base. It already has a base of e. I'm just going to convert this one. I'm going to use the inverse rule, where I can just convert this to exponential. So I would have e to the negative third power equals x. Okay, and that's your answer. So that's your exact answer. And so when you plug it into the calculator, you would get that x is approximately, if you round it, 0.50. Okay. All right. I'm going to do the same thing on this one, where I'm going to use just the inverse property, or the inverse strategy, where this is going to be, log base 10, because it doesn't have anything, so it's base 10. So we would say, okay, well, 10 to the negative 1 equals x. Okay, now remembering exponent properties, anything to the negative power, I just flip it. Okay, so that means that, flip it, make it positive. So that means that x equals 1 over 10. So in decimal form, x would equal 0.10. Okay, so that would be your answer there for G. All right, and so then on h, I have the same base, and there's a minus between. So this can be rewritten as the quotient. All right, so that can be rewritten as log base 6 of 3x plus 14 over 5 equals log base 6, not equal, sorry, of 2x. And because they have the same base, I can just simply say, okay, 3x plus 14 over 5 equals 2x. And solve this for x. I'm going to multiply by 5, and I get 3x plus 14 equals 10x, minus 3x, 14 equals 7x, so x equals 2. Whoa. X equals 2. Okay. All right. Now going to the back page, which is it's more application type. But it uses E, it uses exponential. So it says that a population of certain species of bees in a small public park can be modeled using the following function after t days. So it gives it to you here. And it tells you to find the initial bee property. So if it's initial, that means t equals 0, because 0 days have passed if it's initial. Okay? So I would say, okay, b times 0 equals 900 over 2.5 plus 20 e to the negative 0.05 times 0 power. Okay? So when I simplify that, I get 900 over 2.5 plus 20. Remember anything, well, back up, actually. Negative 0.5 times 0 is 0. So that means it would be e to the 0, but anything to the 0 power cancels to a 1. Okay, so that means that it's 900 over 2.5 plus 20. All right, so I get 900 over 22.5, which gives me 40 bees. Oops, that's supposed to say bees. Okay. All right, and then we get into compound and simple interest, and then whenever we're talking about like half-lives. All right, so I'm going to try to show you the easiest way here to know which one. So this one, the longer equation here, that's going to be your compound. Okay, and this one's going to be your simple. Okay, so what I'm looking for when it says the word compound, for the simple, is if it says compounded continuously. Okay, if it says compounded continuously, you're going to use a simple. So on this example about Jonathan, it says that he invests $1,200. Okay, with a fixed annual interest rate of 7%. Well, that's important. And it's compounded monthly. Okay, so how much would Jonathan have after 20 years? So kind of off to the side somehow, I want you to write this down just as a reminder for yourself. I had to write it down for myself. So P, let me actually make my pen thinner. All right, so P is the principal. Okay. R is the rate as a decimal. N is the, I actually need a thinner thickness here. N is the number of times per year. And then T is the time in years. Okay, so understanding this, all these letters, that's what I want to make sure you understand. So when it says that Jonathan invest $1,200, that's going to be our principal. So we would say A equals 1,200. And then it says 1 plus R. Well, R is our interest rate as a decimal. So if it's 7%, that means it's going to be 0.07. Divided by N. N is the number of times per year. So if it's compounded monthly, that's going to happen 12 times a year. Okay, now this is being raised to the 12 times t, which is the year time in years, so 20 power. And so the hardest part of this is simply just setting it up, because once you get to this point, you can just put that straight in your calculator. And you will get that after 20 years, Jonathan will have $4,846.49. Okay, remember it is money, so make sure that you round to the hundredth, okay? Now, in the simple interest formula, everything as far as what it stands for is the same, but the letter E we're going to use as that number that, it's kind of symbol, if you will. Sorry, the word's not coming to me, but that's in your calculator where you just use E. Okay, so don't try to plug in a number for E. You're just going to use that symbol in the calculator. That's just an arbitrary value that's already in your calculator. Okay, so it says that Nancy invests $6,500. Okay, that's going to be P into her savings account for an annual fixed annual interest rate of 4%. That is going to be R, but R is going to be 0.04. It says compounded continuously. So because it says continuously, I'm going to use my simple formula. So I didn't catch this when I was working it, but it says how much is Kevin's account. Well, it says that Nancy invested, so I'm pretty sure it's supposed to say Nancy. All right, after 9 years. So 9 years is going to be your P. So I'd say, well, A equals P, which is $6,500, times E to the RT power. So times E to the 0.04 times 9 power. And again, you can just plug this one into the calculator as well. And you get that after 9 years, Nancy would have $9,316.64. Okay. All right. 3 more problems, then we're finished. So Sally bought a car for $15,000 through a bank loan. Okay. Which gives a fixed annual interest rate of 16%. So that's going to be 0.16, which would be our R. And it is compounded daily. Okay, so think about how many days are in a year, because that's going to be what N is. And so how much, or what would be the total amount she owes after 13 months? Now, that's going to be T, but I'm just going to convert it as 13 over 12. Okay, I'm not going to put that as a decimal because it's not going to be a terminating decimal. It's going to be a repeating or a irrational number. It's going to keep on going, non-terminating. And so I'm just going to keep it as that. So because it did not say it was compounded continuously, we're going to use our compound interest here. And we're going to say, okay, $15,000 times 1 plus R, but R is 0.16, over N. N is 365 times N, so 365 over T, so 13 over 12. And so again, remember, we can just plug that straight in, and when we do, we find out that after 13 months, the total amount that she owes is actually going to be $17,838.26. Now, you're probably thinking, wait, that's more than what the car loan was from the get-go, but remember, of interest. So because of interest, she's actually owing more. Because of that interest, she has to pay the interest for the loan. All right, so Jack has a pumpkin farm. He invests $100,000 into the company stock holding, but it does say continuously compounded. So because it says continuously compounded, we are going to use the simple interest formula. All right, it says that he has an investment at a percentage of 5.5%. Okay, assuming that the annual percentage, the APY is the annual percentage yield. And so assuming that doesn't change, what will be the total worth of his investment after 10 years? So that's the 5.5 is going to be our R, but we have to convert it to 0.055 because I have to convert it to a decimal. And then T is going to be my time. 10 is going to be my time. So I'd say, well, A equals 100,000 times E to the 0.055 times 10 power. And when you do that, we're going to find out that Jack's pumpkin farm investment, would be worth $173,325.30 after 10 years. Okay. Okay. And the last one. So it's talking about this palladium 100, which is a catalyst. Okay, it tells you that the half-life is 3.6 days. So this is the one where we're going to use this formula over here that already has the half. Okay, it says there's 350 grams in the sample. How much would it have after 21 days? Okay, so in the formula, it says A to the 0. That is the initial. Okay, the initial value. So the initial value was the 350. So in my formula, I have A to this, or A subscript of 0, so 350 times 1/2. T, which is going to be 21, divided by N, so that's going to be how many days, is going to be 3.6. So when I put this in the calculator, I found out that A equals 6.138 grams. All right, so that's how much would remain after 21 days, okay? All right, if you have any questions, please feel free to email me, and I'll answer it as quickly as I can. Now that I've covered it all, you can now go back in and do college part 2 homework, which will go with section 2 notes, and then part 3 homework, which goes over the notes that I just went over myself. All right, so if you have any questions, please.